Hello everyone, this is Mohammed Yaqub and I'm back again with another STM32 tutorial. Has been more than a month since my last video. It was a very busy month and a half for me. So I'm back again, and in today's tutorial I'm going to show you how to use SD card with FreeRTOS. I've been asked by many people to do this particular video and also to do a review on SD card setup, especially after the major update in CubeMX latest version that may have affected the way you'd set up a project and the way you would program SD card with STM32 board. So I'm going to be showing you all that and how you do that with the latest CubeMX version. So without any delay, let's get started and open CubeMX and set up a project for our tutorial. So on CubeMX, in today's demo, I'm going to be using the STM32F7 Discovery board. So this particular board, the F7, it has got a nice 4-bit SD card on it. So on CubeMX, what I want to be choosing is access to board selector. And that will take me to the board selector tool, in which I'll select the F7 board. Alright, and on the board selector menu, select F32, I think, 32F7, and it's the F746 Discovery, this board. And I'll select not to initialize it to the default mode because I want to reset all the pins and enable my own, because I don't want to enable all the peripherals on the Discovery board. Alright, and on the pinout, the first thing I'd like to do is to clear all the pinouts and enable only the necessary ones that I need for my tutorial. And the first thing I'd like to enable is the Debugging Uart, because I'm going to be using serial terminal to print debugging data. So to test if the SD card is opened successfully, then I want to print something to the terminal. And for that, I need to enable Uart1 on the F7. Let me show you what I mean. So when you go to the user manual and scroll down to the ST-Link schematic, you'll find a virtual comport Uart. So that will be on this ST-Link schematic, and that will be this particular one. So virtual comport RX and TX, and I'd like to find out which pins correspond to these virtual comport. So let me search for the virtual comport TX, and I already know that in advance because I have done that before, but I want to show you how you find that out if you are using a different discovery board, for instance. So virtual comport TX, that is on pin PA9. So let me get back to my CubeMX and search for PA9. So PA9 is this particular pin, and that's on Uart1 TX. So let me enable that temporarily. That will be on yellow color because I haven't enabled the peripheral just yet. And then now let me find out the RX too. So virtual comport RX, and I know that it's on BB7, but let me verify. So virtual comport RX is on BB7 indeed. So let me search for PB7 and enable that. It's on Uart1 RX. And now all I need to do is to head to peripherals and go to connectivity and search for Uart1, this one, and enable the mode and set it to asynchronous. And as soon as I do that, you'll see the yellow color turning into green, which indicates that it's fully enabled. So exactly. So now Uart1 is fully enabled, and I don't need to use DMA or interrupt or anything like that because I'm going to only be using Printf to use that Uart. So I'll leave it as default. And the second thing I need to enable is the SD card. Basically, I don't need anything else. So for SD card, it's part of the connectivity as well, and that's SDMMC1. And select the mode. So you can either select SD 1-bit or 4-bit. It doesn't make a difference. We'll use exactly the same setup for RTOS. So I'm going to be using a 4-bit mode because that's the difficult one. If we got it to work on 4-bit mode, it will certainly work with the 1-bit mode. And by the way, 4-bit mode is faster than 1-bit mode, of course, because it uses 4 data line as opposed to 1 data line for 1-bit. So I want to select 4-bit mode, and that should enable particular few pins on here. And I would like to verify that it enabled the correct pins. So let me get back to my user manual and go to the SD card schematic just to see the pins and note them down and compare it to the one enabled automatically by the cube. So I think I need to scroll up a little bit into the peripheral schematic. Let me find that out exactly. So that's the SD card thing. And according to schematic, that's on micro SD D1, D0 to D3, clock and command. Let me find these pins out and see where they mapped out to. So micro SD, I want to search for this in here. And that took me down to the microcontroller schematic. That's what I need. So micro SD data 0, 1, 2, 3, and clock are mapped out to BC 8, BC 9, 10, 11, and 12. Let's verify that on the cube. So when I look at STM32F746 data, so all the data lines are on BC 8, BC 9, BC 10, BC 11, exactly, and the clock is on BC 12, so that is correct. And for the schematic, I just need to find out the command, and I know it's on the top somewhere in here. There we go. So micro SD command pin is on PD2. So let's verify that out. So that's the command, and it's indeed on PD2. So we've got the correct pins mapped out physically on CubeMX. So we can now carry on. Right. So the first thing we'll do here on the SD card parameter setting is that we might want to change something. No, we don't want to change anything here. And a very important thing, when using 4-bit mode, whether it's with RTOS or without RTOS, you need to enable DMA. So go to DMA settings and enable TX and RX DMA. So that's RX, and add another one to enable the TX DMA. And leave everything else by default. And then we also need to enable SD card interrupt. So SDMMC1 global interrupt needs to be checked, whether using RTOS or no RTOS. Whenever using 4-bit mode, you need to do DMA and interrupt enable. And now all is left is to enable FreeRTOS. We have completely set up SD card and SDMMC settings. All we need to do now is to enable our FreeRTOS and start enjoying our FreeRTOS application. So I'm going to head down to middleware. Excuse me, I forget one thing. We need to enable FATFS file system for the SD card. So on middleware, FATFS, check SD card because that's the one we have enabled. And on the configuration, we also need to enable, I'm going really quick so I forget a few things, so excuse me with that. So use DMA template has to be enabled. Okay, whenever you're using 4-bit mode, you have to use DMA template with the FATFS as well. So that's one, and I think we'll leave everything else as default. Apart from the sector size, we want to set the maximum to whatever maximum is available, and we'll leave the minimum to 5.2. That's pretty much everything we need to do with the FATFS configuration. Next thing is to enable FreeRTOS. So on FreeRTOS, I want to enable the whatever version is available, and I've got only version 1 for this one. And the configuration, I'll leave everything as default. I don't have any particular configuration in my mind. If I have different applications where I use queues, timers, then I might come here and enable a few tools that I need. But for this application, I pretty much don't need anything additional on top of the default settings. So I'll leave them as default. And then in task and queues, I will just use the default task. I don't need to add an additional task. I'll be using the default task for my SD card. So I'll leave it as default. I might just want to increase the stack size just to be on the very safe side, although I doubt that I need more than 128. So I'll leave it as it is. If I ever needed additional stack size, then I'll increase it to 256, for instance. But I'll leave it as it is for now. And that's pretty much it. So I don't need to do anything more with the FreeRTOS. I've enabled it, and I've enabled my FATFS and my SDIO peripheral. Now, just very few things. I want to enable the external oscillator. So I'll go to System Core, RCC, and high-speed clock, and use the ceramic resonator. And I need to go to clock configurations and set up my clock. For the F7, it's very tricky to use the automatic clock resolver. It can take a lot of time and it may not find a solution. So with the F7, I always like to use manual settings. So I know the external clock frequency is 25 megahertz, and I know that from the schematics. So I'm going to select the external oscillator, and I would like to set these manually, and I have settings here stored from my previous project. So the PLLM is 25, so M set that to 25, and I would like to achieve the maximum clock speed of 216 by doing that. And then the next one, the prescaler, is 432, so this N has to be 432, so find that out. Okay, so 432, that's the maximum pretty much. And then P to 2 and Q to 9. So set the P to 2 and the Q to 9, and select the PLL 48 megahertz clock for the STD-MMC. Sorry, for the STMMC rather. I'm sorry. All right, and it seems like that's pretty much everything. We've got the maximum clock speed, we have the clocks within the range, and everything is set up. So that's our clock configuration done manually. Just a quick recap in here. Yeah, one additional thing, since we're using FreeRTOS, it's recommended that you don't use a sysdig interrupt for the time base. You'd rather use one of the timers. I like to use timer 6 for that. Okay, so that is pretty much everything, I think. So let's head back to Project Manager and generate our project. So I would like to store the project in this particular location, SD card RTOS, and I'll call it SD card RTOS tutorial. I'll store it at this location. My IDE, I'm going to use Keil version 5 for this, and that's it. So click on generate code. I'll click yes on this. And for any of my business consultancy contact on STM32 programming or embedded systems, you can get in touch with me through mutexembedded.com. So for now, let's wait for this to generate the entire code, and I will go on my list. This list explains, this is a preparation list I made, explains what are the steps that you need to go for this tutorial. So I'm going to copy some stuff from the list, add it to the IDE. For the time being, let's just wait for the code to generate. Alright, code generated successfully. Click on Open Project, and this will take you to Keil IDE. And on Keil, the first thing I'd like to do is to compile the code and start adding the necessary setup code and includes while the code is compiling. Because for the F7, my PC, it takes about 5 minutes to compile the project, so I will start adding my includes. And on my list, the first thing we need to add is a couple of header files for the standard I/O. That's to be able to use a printf, and the second one is string, so that to use mem copies and things like that. So let me copy these into my project. I'll put them into the begin include section, and then the second thing is to add the printf function. So I have a separate tutorial on how to use printf, and I explained what are these that you need to include. So I'm just going to copy them over to my project so that I enable using printf with UART1, which is my debugging terminal. So I'm going to put the prototype code in here and the definition of the function down into begin number 4. So in begin number 4, I want to add this to link printf to my UART1 for printing debugging data. And then next thing we need to do is to add external variables. Those are for fatfs. You'll find these variables defined into the fatfs.c file. So when you open fatfs.c, you'll see these variables, and these are library defined for SD card hardware level functions. So I need to define those into my main as external variables. So let me copy these into my main. And I'll add these in bigger number, I'll add them globally in bigger number 0. So these are SD card variables for fatfs. And then next thing on the list is to add file IO variables. So if you have used file IO's library in C before, whether with STM board or with other platforms, you would have to define something called fresult to store the result of the fatfs communication. You need to have an unsigned 32 perhaps for bytes written and bytes read in case of f read and f write. And you need to have 2 buffers, one for writing data and one for reading data for testing. These are pretty much flexible. You can change the names, you can change the types as well reasonably. So let me copy these into my main, and we will use them down in there when we start the file operations. So these are very, very simple variables. All they're doing is these are the file IO operation so the file IO variables rather. Okay. And I'll be using the write text to write data to the SD card and rtext buffer to read data from the SD card and perhaps display it into my terminal. And then next I can start doing the file operations. So the first thing is to mount the SD card. So let me copy this over. So this one is, we'll add this code into our thread. So into our default task, which is this one. This will do the FreeRTOS initialization, and now we can start using the SD card. So step number one is to mount the SD card. And I'll put the mount to 0, so you don't have to wait, you don't have to check, it will always succeed. I will try to mount it as soon as it can. So I don't need to check if this succeeded or not, because it will always return me OK. So that's mounting the SD card with this SD path defined by the FreeRTOS variable. Okay. And by the way, could just finish compiling successfully without any errors. We'll recompile it now as soon as we add the additional code. So step one is to mount the SD card, and step two is to open a file. So I want to open a file in the SD card for writing data. So step number one. So now I want to test write. So open file for writing, and this section is for testing write operation. Okay, and the function is called if open, and it takes few parameters. So if open is a function, and it takes a pointer to the SD file path and the name of the file that you want to create, and what are the open access variables. So I want to open it for create. If it doesn't exist, I always want to create it, and I want to open it for a write access. So in fact, let me just copy this over entirely. It's very simple. So opening a file for writing, I want to check if this one is equal to OK, then I carry on. If not, then I return an error. So if this one is not equal to FROK, which is the status return, then I want to print something to the terminal. I want to print perhaps failed to open file for write, or failed to open write file. All right, and if everything okay, then I carry on. So if it's equal to okay, then I want to printf opened write file successfully. Okay, and I will continue. Next step is to write actual data to the file, and to write data you need to use this fwrite function. The fwrite function takes the same SD file pointer, and this pointer is defined at the top. I define it as a file IO variables, or it's rather one of the extents for the FreeRTOS variable. So this is the SD file object for SD card, and it's of type FIL. If you have used file IO library in C, even without STM board, you will be quite familiar with FIL variable type. That's for the file pointer. And then I can start writing data to my SD card with fwrite function. It takes this pointer, it takes the pointer in which you want to write data from, and the length of the data, and then a pointer to the bytes written. So this would return you, if you are expecting to write 100 bytes, and this only written 50 bytes, then this will return you 50, and it returns the status. So I'll copy it entirely. So this one, write data to text file. So res is the status variable we defined at the top. So let me scroll up. Yeah, so this is the result to store the SD card write and read operation status. All right, so we have passed the SD file pointer, the write text. So this is the text we want to write. Has to be defined at the top. There we go. So this is hello from Mohammed. I want to say SDIO DMA RTOS, something like that, and this will be written into my text file. All right, so I open a file, I call it F7 file 1 perhaps, and I want to write to it the data I've written above and the length of the data, and this is a pointer to the bytes written. So just bytes written is defined at the top as well. It's the file IO variables in here. So this will tell me the actual bytes written. Okay, and after that I want to check if the bytes are more than 0 and the status is if the bytes are 0 and the status is not okay, then I know there is something wrong. So I want to make this quick check and printf to my debugging terminal. Okay, so that's a very simple one. And then if everything is okay, then I want to print a file written successfully. Okay, and perhaps I also want to print the actual data written. Okay, so in addition to printing the status that is written successfully, I might want to write print also the data. So something like write content is equal to, I want to pass a string of my write text. All right, and that should print that to the terminal. It should print me whatever data printed to the text file. And then I will close the file because I'm done with my write operation. So once done, I will close the file. And then, so that will be testing the write operation. So let's do a quick test for the write operation, and then we'll come and continue with the read operation to read whatever written to the file. Or in a matter of fact, let's do them in one go. That will be a lot easier. So next, you want to do a test read files. So I want to test file reading this time. Okay. And I'll do that really quickly. Let me just copy that over. It's very, very simplistic. You already got the idea of how to use file IO. So I'm opening the file. It's called f7file1.txt, and the access is only read. I'm just resetting the R text buffer. So this is the buffer that is going to store my read data. And then I'm reading this. I am requesting a maximum size of 200. So when you go above, the read buffer of size 100 rather, and I'm requesting the maximum size, but the read function is clever enough. It will open the file or try to read 100 bytes, but maybe the content is only 20 bytes or 25, so it will only read the 25 till the end of file, and it will return me the bytes actually read. And then I can use this variable to print the data and things like that. So I want to check if the bytes is equal to 0 or any error, then I know I failed to read. If it's successful, then I'll print file read successfully, and I will print the file content read from the file. So very similar to the write operation, but except this is a read this time. So let me now compile the code and do testing. So I expect to see successful things onto my debugging terminal if everything is okay. And then I will plug in the SD card to my PC and read its actual content. So before we start, let me just plug in my SD card just to show you that I haven't got any files on it. So open my SD card. So it has got the previous one. Let me delete it. So I haven't got any files stored in the main path. So I close it. I'll plug it in back to my STM board. And let me, code is compiled without any errors, so let me load the code to the board, and I'll open a serial terminal. I'll open real term, and I know the COM port is the only one, COM port 6, and the baud rate I set it in CubeMX to 115200. And now let me reset my STM board. And here we go. There we go. So opened write file successfully, file written successfully. Write content is hello from Mohammed, SDIO DMA FreeRTOS, and file is actually read successfully, and it says file content is hello from Mohammed, SDIO DMA FreeRTOS. That is amazing. Now let me plug in my SD card again and see the actual content of the SD card. Alright, just plugged it in, opening the SD card. And here we go, fantastic. I've got the f7file1.txt, and guess what? It has got my content. So congratulations, you got your SD card working with FreeRTOS. And this brings me to the end of my tutorial today. Thank you guys for watching, and as always, if you found it helpful, don't forget to hit like and subscribe. Thank you, and I'll see you in the next video. Bye bye.